Thermal expansion sample problem for a spring example. In this example, we do have a configuration of a bar, which is made of A992 steel, has a diameter of 1/4 of inches, the diameter of the pipe, the diameter of the rod, and 4 feet in length. Before fixed support, this time we do have two spring with a K of 1000 pound per inch. At temperature of 40 degrees Fahrenheit, there is a small compression inside each spring. So it means when the bar is relaxed, when the rod is relaxed or at rest, there is a 0.5 inch of compression inside the spring. So a spring is not relaxed even at the initial condition. Then we raises the temperature from 40 heated up to 160 degrees Fahrenheit. And when the temperature is 160, we want to determine the forces in rod. Let's see how to approach this problem. Because our problem is a symmetrical shape, we approach the problem by just considering half of the structure. So it was a rod of 4 feet. We just consider 2 feet of the rod from. So this is our center line. We consider from the center to any of the. So that's our center line. And moving to the right. So that's 2 feet of length of the rod. And we just call the distance between the end of the rod, so a start of spring to the start of the support, a distance of x. We can call it initial condition, initial. Then we call it phase 1. And we call this part phase 2. So at the initial from the center line to the support at the right, it's a fixed support at the end, at the right end. So if we release that support, the thermal expansion lets the rod goes all the way to the right. So that's phase 1. So that's the departure point, and it just goes all the way to the right in phase 1 when we remove the support at the right, and that's just due to temperature. That's delta T. And because in the reality we had a fixed support at both ends, we need to replace back the support. So as if we replace back the support, there is a push on the spring and it just pull the bar to its original location. We call that delta F. That's delta due to the force of support. And the same, if you study the free body diagram of this part, you can see the free body diagram of the right support shows, based on Newton law, it just shows the same amount of force applies to the left, it applies to the spring and cancel with Fs, so with F. So F is equal to F spring. Mhm. And also F rod. The same force a mutually applies to different part of this configuration. Let's approach the solution to see how what happens in the problem, uh, in solving the problem. So again, due to symmetry, we just analyzed half of free body diagram. Mhm. Then applying compatibility, which is a key to solving this kind of problem, and it just says the amount of departure when in phase 1, when we remove the support at right, it's delta T, deformation due to temperature, minus delta F minus deformation, subtracting that from delta F, which pushes back the spring and bar to its original location, goes by nothing but a amount of X. Mhm. So that's our X, and that's due to compatibility of the formation. So if we know delta T is equal to alpha delta T times length of the bar, so that's replacement of the numeric value of thermal coefficient expansion times different, it rises from 40 degrees to 160, times 2 feet, half of the length of the structure of the rod, times just conversion of feet to inches. Each feet is 12 inches. And delta F is Fs over times L over EA. So in denominator, we have a quarter pi times 0.25 squared times the modulus of elasticity of A 992 steel, which is again 29 times 10 cube KSI. And at the top, let's observe this is the length. 2 times 12 is the length of half of the length of the whole rod, total whole rod. And this is let's study this part. Mhm. We this time we focus on Fs. Mhm. From physics, we do remember force of a spring is equal to a stiffness of a spring times delta S. So a stiffness is provided to be 1000 pound per inch. Converted to kilo, it's 1 k pound per inch for consistency of our solution, because we have everything in KSI. So let's have it in 1 times 1 KSI, kilo pound per inch, times X, which is the distance we were interested in to calculate it, mhm, plus 0.05. You remember there was initial compression inside the spring, mhm, and plus so that's initial compression, and X is distance of travel, to the support. So if we want to know what delta S is X plus initial compression. So that's times Ks, that's our Fs. We are replacing that on top here. So that's 1 KSI times X plus 0.5. If we solve the problem for delta T and delta F, and both of them, subtraction of them is equal to X, one can easily say X is equal to the thermal one minus force of a spring over FL over EA. The same force to the spring applies to the rod due to a mutual interaction between the support and the spring. mutual interaction between spring and rod. So x is the only unknown of the problem. We have one x here, and we have the initial one over here. If we take them both side in one side and then solve it for x, it will give you x is equal to zero point zero 0.01 almost inches, and replace that in force formula, it gives you a point 0.5, almost 0.5